in the year 2019 as a part of India Train to Program for Advanced Research. Dr. Chirakkal joined Space Application Center ISRO in 2015. His research interests are in the advanced areas of synthetic aperture radar, such as pulsar, INSAR, POLENSAR, as well as nonlinear dynamical system theory and mathematical ecology. He has published several articles in international journals, conferences, and technical reports. After joining ISRO, Dr. Sanid contributed significantly toward development of an indigenous SAR data processing software suite, which is known as MIDAS. It stands for Microwave Data Analysis Software. Additionally, he has played a key role in developing an end-to-end Python-based DINSAR processing tool for ISRO SAR missions and a POLENSAR module for forest height retrieval of Indian forest at SAC. Dr. Chirakkal received the Indian Society of Remote Sensing National Geospatial Award for the year 2020. Now, without further ado, I would like to welcome Dr. Chirakkal for his talk.
Thank you, Dr. Mandal. Before I start, can I just get an info about the audience, like how many people are there and from what background they are, just very briefly.
Basically, audience are some audience from the faculty, some are from the PG students, some PhD student, and something are for the final year BTech students.
Okay, so all are from computer science or what is the area?
Maybe some of them are electronics communication also.
Okay, sir. Okay. So there are some portion are faculties and most of them are students, right?
Right. Most of them are students. So you teach it into the fundamental level, no problem, sir. Because this is the area which is not very well known for many of us.
Okay, sir. Okay. The slides are visible, right?
Yes.
Yeah. Okay. So
you can make it full screen.
Okay. Yeah.
Yes, great.
So let me just introduce to this area. This is actually, I mean, after I joined ISRO, I have been working on this area for some years now. It's a very interesting area, and I hope in this 1 hour lecture, I'll be able to give you some glimpse into the field and also to motivate some of you to take up research in this area. So that would be my objective, not to teach you the whole area. It's really vast, and and I myself, I'm still learning about this area. So we'll try to do this together. So, and also, what is the format of asking questions? I would prefer if audience, whoever asks questions, ask immediately without waiting for me to finish. Yeah, I don't know what is the format followed.
So there is no hard and fast format. If the audience like to ask question, you can allow them to ask question, no problem. As you have already announced,
they are free to ask question. Basically, I am not muted to anyone. That is just mute, and they can unmute themselves and ask the question.
Right.
Yes, sir. Yes, sir. So I encourage everyone, please ask questions, because that will make more sense for me to answer your doubts rather than me going on about this thing. Okay, so let's start. So I have written something in a little bit informal way as the dark arts of phase manipulation. It is, if you work in this area, you will understand that what makes this different is actually the phase information which is available in the data. So I'm not going to talk about what is synthetic aperture radar and all those things. That will take another lecture from someone who is doing in that, working in that area. So I'm assuming that you have some very basic idea about SAR, or else I will just tell you in 2 minutes what it is. So, optical images, which most of you would be definitely familiar with, like Google Earth images and all those things. They are taken from a camera, right? I mean, it's basically just a photograph, but taken from a very special camera. But the physics is the same. It is just collecting the light and forming the image. And the wavelength are in the visible range. So it's a visible light that is being collected and that is being used to form the images. And this high-end camera is positioned on a platform which is orbiting around the Earth. It's on a satellite. So, and also this is very similar to hyperspectral. In the case of hyperspectral, we stretch the wavelength beyond the visible range, some to this side and some to that side. And also we make the interval with the delta lambda, the difference between two channels, also pretty small, so that we have a lot of bands and we have this information. Now this radar remote sensing, instead of hosting a camera, we host a radar on the satellite, and it basically functions on the basis of the principle of ranging, right? I mean, whatever you send a radar signal, which is in a microwave, this is a completely different wavelength from other optical or hyperspectral. This, we are talking about 1 to 6 gigahertz for these P to X bands. I mean P to C bands. But I mean, I'm just trying to tell you that this is a different wavelength we are sampling. And because of that, and also another important thing is here we have our own source of energy, right? So for optical, you need sunlight. Basically, the scene is illuminated by the sunlight. And the sensor just collect the reflected and scattered light. It's a passive sensor. Here we have an active sensor in the sense that we have our own source of microwave. We send the microwave, then we collect the back scattering. Whatever the microwave hits the target and whatever is scattered back to the sensor, we collect it and we form an image. So I hope this you understand from the very beginning. And why the phase comes into picture, because since it's an active system, it's an active remote sensing system as compared to optical, which is a passive system. We are sending the microwave, so we can tightly control the phase of the transmitted wave and also the polarization of the transmitted wave. So in this way, we have a constant phase relation between transmit and receive polarizations, and this phase information is consistently maintained throughout the operation of the radar. So we have a coherent system. That means every pixel of the image is now containing the information not only about the scattered power, that is basically what you get, right? In the optical, you know the information about the scattered power or the intensity or radiance or whatever. Here we have, on top of that, we also know the phase relation between the transmit and receive wave. That may, and you know from engineering basic courses, whenever you have a quantity which has a phase as well as an amplitude associated with it, you automatically get a complex number, right? Because that is what complex number is. It has these two dimensions of information. So that means the image what we are receiving in the case of SAR, that is a spaceborne radar. I'm talking about the synthetic aperture part. It's not relevant right now, but just assume it is a radar which is positioned on a satellite, and you get this kind of data where every pixel is a complex number. Now that complex number contains amplitude and phase. Now, when you do the amplitude analysis, that is known as the sigma naught normal analysis, backscatter analysis, you can do a lot of things. I mean, that is how this area was growing for so long. But what happened was recently, not very recently, like for some time, like because of this additional information, that is a phase, people were trying to use that on top of the amplitude information, and we get into these kind of areas. These are called SAR, INSAR, POLSAR, and POLINSAR. So INSAR is SAR interferometry, POLSAR is SAR polarimetry, and POLINSAR is a combination of both. I would like to talk about all this, but I mean, each of them are quite detailed. So here today we'll talk about POLSAR, and I will introduce a little bit of POLINSAR because I'm currently working on that area, and it's quite fascinating. So we'll take baby steps. We'll go with some very fundamentals of what we are talking about, the how to describe polarization of a wave, and how can we theoretically position ourselves to understand scattering of a microwave signal. And decompositions are a very important area in this, and we'll do a lot of applications. So yeah, so I mean, this is I mean, whenever I talk about this area, I try to introduce some books, because I mean, from 1 hour you won't be able to understand much, but you can always go back and get these books. So if you are in an organization or in a academic institute, you can always ask your library to purchase these books. This one particular book is really good. This is from the masters of this area, Portier and Lee, and this gives you a mathematical overview of the whole subject. This subject is a bit mathematical, that you will come to know, but it's not too bad. I mean, if you have some idea, some understanding of linear algebra and some understanding of electromagnetism at the college level, this area you will be able to grasp. And another book which is not very mathematical but gives you the overall concepts very clearly in a very nice manner is the Van Zil's this book. This also you can try to get your hands on. And of course, you cannot talk about microwave remote sensing without Ulabi. I mean, this is like the Bible of the area. This book is really huge, but this has everything you need. Like if you are a researcher who is going to do your PhD in this area, this book is a must. Or I mean, even if you are a faculty who is going to teach this area, this book is important. You can't do without this book. So I don't know how I should go about with this equations part, but I'll just try to explain in a very basic manner. So basically, you may be aware that electromagnetic wave is elliptically polarized in general inside a linear medium. So this is sort of the idea behind it, why people say so. So, you know, like in a transverse wave, the wave is propagating in some direction k, that is a propagation vector, right? K, vector k. And the electric field is always perpendicular to that. This is very basic understanding. I hope you all agree with me. And in that plane, it is the electromagnetic wave is in a plane confined to a plane perpendicular to k. And since we do this in the complex formalism, like the electric vector and the magnetic vector, I mean, they are treated as complex numbers. You basically end up with a 2D complex vector to describe the wave in that particular plane, right? And when you write the equation of that and you try to eliminate the other extra parameters, you end up getting an equation of an ellipse. So in a very generic sense, electromagnetic waves are elliptically polarized. So but ellipse, I mean, you should understand, circle is also an ellipse, and the straight line is also an ellipse, right? I mean, you can change the parameters of the ellipse, make it very elongated, very elongated, that it looks like a straight line. And you can also manipulate the skewness or the ellipticity of the ellipse, and you can make it a circle. So circular polarizations, linear polarizations are all special cases of elliptical polarization. It's a very generic case. So I mean, why do I say, I mean, how do you imagine polarization? So polarization is nothing but, so when we talk about electromagnetic wave, there are two vectors, right, which is oscillating, and that's how the wave propagates. But we don't really think about magnetic field in this area of remote sensing unless the scattering material is itself magnetic, like diamagnetic or paramagnetic or something. So we only focus on the electric field because that is what we see, that is what the sensor senses in the case of microwave. So the electric field, which is, as I just said, is oscillating in a plane perpendicular to the direction of propagation, which if that direction, the oscillation, the tip of the electric vector which is oscillating, if it is tracing out a straight line in time, so the k is the direction of propagation, you take a transect, you take a cut, you take a plane perpendicular to it, then you observe in time what is the tip of the electric vector doing. So in this case, you can see the wave is propagating in some direction. So I don't know whether my cursor is visible. So you can see the wave is propagating like this and the electric field is oscillating like this. So, but if you take a constant cut, you take a plane, then you don't change the plane. You just wait in time. You see in time what is happening. Then you see that the electric vector is going up, coming to zero, going to the negative maximum, coming back to the zero, all in a straight line. So a wave which is propagating like this is linearly polarized because of this situation. This is a line, that's why it's linear. Whereas you take two electric fields, you put them one in X and one in this case, Z direction, and then you make them 90-degree out of phase. Then you observe what happens to the tip of the electric vector. I don't know this is whether you are able to follow this, but if you think it through, like this is a very nice exercise. You can do it in Python. It's very simple, like in a few lines of Python or MATLAB. You can see that if you offset the Y electric or the Z electric field as compared to the Y electric field, you give it a phase difference of 90-degree, you see that the tip of electric vector start tracing a circle in the plane perpendicular to the direction of propagation. So this is the circularly polarized light, where literally the electric field vector is rotating as the wave propagates. So I mean, what I'm trying to do here, I mean, you please try to get the big picture. I'm just trying to get the descriptors of the polarization, how to describe the polarization state of a wave. So as I said, in general, this is an ellipse. Now the ellipse can be characterized by two angles. One is the ellipse orientation angle psi. So this is with respect to horizontal. So in this parlance of remote sensing, instead of X and Y, we normally call horizontal and vertical. These are the two directions which is fixed with respect to the sensor. So the antenna, the SAR antenna. So whatever the polarization in general, the ellipse could be oriented away from the horizontal direction by an angle psi, and it could be skewed by an angle chi. So this psi and chi, these are the ellipticity and orientation angle, defines completely the polarization ellipse. So you can see special cases here. For example, if the chi is 0, that means it is a very narrow ellipse, right? It is a straight line. As chi approaches 0, chi tends to 0, it becomes a linearly polarized light. And when the psi is also 0, it is a H polarized light, because the line in which the electric field is oscillating is now along the H direction. If this psi is 0, that means the ellipse is completely tilted in the H direction, right? So that's how, like, you can get all other situations from these two angles. And also when chi is 45-degree, you get a perfect circle. You get a circularly polarized light. So another way to characterize, so as you can imagine now, because psi and chi, there are infinite possibilities. So there are infinite polarization states. You can do a nice mapping between the psi and chi and something known as the Poincare sphere. So this sphere is known as the Poincare sphere, and every point on the surface of this sphere is a polarization state, and the orthogonal polarizations are antipodal. That means you take one point, and if you want to know the orthogonal direction and the orthogonal polarization to that point, you just go to the other end of that point. You go to the antipodal point. For example, if you are on the North Pole, this is left circular. Now the orthogonal state would be right circular. Then you go to the South Pole to get that. So this is how we describe the polarizations, either using the Poincare sphere. And Poincare sphere, as you know, a sphere can be characterized using two angles, right? Given a fixed diameter, the chi and psi, in the description, this chi and psi are the same, what we saw here. This is the same chi and psi. So this is a one-to-one mapping. And this G0, G1, G2, G3, which gives you the coordinates on the surface of the sphere, is the Poincare, sorry, is the Stokes vector. G0, G1, G2, G3 is the Stokes vector or Stokes parameter. So in this area of SAR remote sensing, you will hear a lot about Stokes parameters, Poincare sphere, ellipticity, and orientation angle. So just understand that these are the way to characterize the polarization state of the transmit or receive wave. So there is nothing more to it. This is a complete formalism to completely describe the polarization of wave. Now we come to the scattering. So what happens is we now know. So what is our understanding now? So we have a microwave source which we know what is the transmit polarization. We have tight control over the phase of the transmission. Now this particular microwave, electromagnetic wave, propagates and it hit a target. Now the SAR is such as is a system which only collects backscattering. So it will not go in any other direction in space and collect the scattered signal. It will stay exactly where it was, and it will collect the signal which is coming back to it. This is the backscattering. So we have to correct for the propagation to the R square, because that's how the power decreases when you have a spherical source. Then you have to again you have to account for the propagation, I mean the diminishing of intensity when it come back. So there is 2 R square terms, so it becomes 1 to the power R to the power 4. I mean 1 over R to the power 4, and whatever is modulating this transmit power and the receive power is the sigma. This is the radar cross section. And if you normalize it with the area, you get the radar cross section per unit area. That is the standard sigma naught of this area. So sigma naught is what people study normally when you want to characterize the. So it is like a probability of scattering, like given a unit area and given this particular incident radiation, what is the probability of scattering? That is what it tells you, the normalized radar cross section. And it changes, like if you have very rough surface, there will be a lot of scattering, because microwave, again, I forgot to tell you in the beginning, since it's a completely different, it is located in a completely different location of the electromagnetic spectrum, the physics of the scattering completely changes. So when you have optical, for example, what is happening? Optical, the photons of the light is basically exciting certain chemical phenomena, right? I mean, the energy levels between two electronic levels in an atom, that energy required to, for the electron to jump up and down is actually in the photon, I mean, the energy of the optical photons. So it basically excites those kind of phenomena. Whereas microwave, being a very, very larger wavelength compared to optical, it has the photons of it has no such power. It cannot excite any atomic phenomena. It can only change the rotation or the vibrational quantum levels. I mean, it can excite between them. So that's how the physics is completely different from optical. That's why it senses different properties. This is important. So normally when the colors, that is what the optical camera records, right? It's the colors. It's basically talking about some chemical, it's talking about the constituent, the chemistry of the scatterer. What is it made of, the constituents. Whereas the SAR gives you no such information. It could be, you may be measuring some complicated chemical with different properties, or as it could be a homogeneous rock, but if the shape and the dielectric constant are similar, you will get a similar SAR signature. So SAR is more sensitive to dielectric constant, geometry, roughness, moisture, because moisture changes the dielectric constant drastically. So it gives you a different set of information. That's why one cannot replace the other. There is a big debate in this remote sensing community, SAR versus optical. I think the debate is completely bogus. I mean, the information both are giving are completely different. One complements the other. There is no competition. So this is the case for a single point target, and if you have a extended target, you need to, as I said, normalize with the area, so the integration comes. Now this is what I have been talking about, where we are not talking about the polarization. There is no information about the phase, right? So this is you can call a scalar formalism, where the electric field is basically the power of the electric field, and we are not talking about in which plane, in which direction the electric field is oscillating. No such information is here. The equation is a scalar equation. But we can vectorize this, where we take care of all the vector nature of electromagnetic scattering. Then we automatically end up in SAR polarimetry. So that's what basically it is. You don't throw away the information about the polarization state of the transmit and receive electromagnetic wave. You retain them in your formalism, then you end up getting this area of SAR polarimetry. So this is the vector approach to electromagnetic scattering. So instead of sigma, which was a single number in this case, equation 6, now we have a matrix, S11, S12, S21. This is a 2 by 2 complex matrix, and it's a complex matrix. That's important, because as we saw earlier, the electric field, the x and y components of the electric field are themselves complex numbers. Because when you may be remembering, when we do this solution to Maxwell's equation, the electric field, magnetic fields are complex, and the permittivity is also complex, the dielectric constant. Everything is complex numbers. So S11, S12, these are complex numbers. So instead of a one real number, you end up getting a 2 by 2 complex matrix. This matrix, which again mediate the EIES, is the incident Jones vector. That is basically the descriptor of incident electromagnetic, incident electric field. And ES is the scattered electric field, and E minus JKR divided by R. Now there is no square, because now we are talking about amplitudes, not the power. So the power goes as 1 over R square, but the amplitude dies as 1 over R. So this is a propagation term. And what else is mediating EI and ES? It is just this scattering matrix S. So this is the scattering matrix. And if it's a point target, people also call it a singular matrix. And this is the starting point of SAR polarimetry. So when you have a fully polarimetric SAR system, the information, what is given to you when you purchase or when you download a fully polarimetric SAR data, you are getting the scattering matrix. That's 4 channels, HH, HV, BH, BV, which is same as S11, S12, S21, and S22. So this is the scattering matrix formalism. So if you have this S matrix, you can do a lot of stuff. I mean, this is where the area is quite rich. The field is quite rich. So I'm just going to show you one thing which you can do. I'm not focusing too much on how it is derived. What I want you to see is this graph. So this is from a standard target. So this is from a trihedral corner reflector. So you see the X and Y axis, we have our old friends here. So we have the psi and chi angle. So these are the polarization descriptors. Again, we are again coming back to that. That means every point here in this XY plane, that is a psi chi plane, is a polarization state. And on the z-axis we have the power. So what is it showing is SAR actually measures 4 combinations of transmit and receive. So the horizontal transmit, horizontal receive, horizontal transmit, vertical receive, vertical transmit, horizontal receive, and vertical transmit, vertical receive. So it is basically sampling 4 points of the Poincare sphere, right? But there are infinite possibilities. I can transmit in 45-degree angle to horizontal, or I can transmit circular, I can transmit elliptical. So how can I get the scattering response if I transmit in any other polarization which is not in this equation? So the power of SAR polarimetry, one of the most important thing is that if I know the power or the scattering matrix in this basis. This is called HV basis, the standard horizontal vertical basis. I can get the scattering matrix in any other basis by doing a unitary transformation. So that means that's quite remarkable if you think about it. Like we can construct or synthesize information about any other transmit and receive combinations if we know these four. So that's how I could do this. So we have synthesized power if I transmit in any other combinations. So I hope you understand this. So this is one thing, one property that makes our polarimetry quite useful, because horizontal vertical may not be the optimal basis for my problem, right? I mean, I may have my study area or my pixel may be having orientations in some other direction, and decomposing in that, in that particular skewed directions would give me more. This is similar to PCA, right? When you do principal component analysis, you want to see which direction has the maximum information. You want to do the Gram-Schmidt orthogonalization. So that way you can think of that way here also. So and these are quite nice. I mean, this is for another polarization response from another standard target. This is a dihedral corner reflector. I'm not going into details of why they're known as standard targets and why these names mean, but just understand that these standard targets, we know what should be the polarization response. We know 100% theoretically. There are perfect models of it, and they're made from perfect metallic surfaces, of which microwave is very reflective. So metal is like mirror for microwave. It reflects maximum. So in that sort of standard target is used for SAR calibration. We deploy them on ground, and then we see the response from them. Then since we know what theoretically, ideally what should be, we can correct for any distortions. So we started with the descriptors, and we went through scattering. Now scattering, just to motivate you, is the core of this area. Like we need to understand it in much detail. Like there are surface scattering models. Like if there is a surface with some kind of roughness, how can you model the microwave scattering from it? And if the surface is small, you can do certain approximations. Then you end up getting what you know as small perturbation model, SPM. Then if the roughness is more, you can't use SPM. Then there are more complicated models. And I mean, one of the current industry standard is what is known as I2EM. That is the improved integral equation model. So that will give you the surface scattering. But if there is a volume, like if there is a random scatterers scattered in a volume, then the scattering is not from the surface of it, it is from the bulk of it. And that is known as volume scattering. And there are models for it based on radiative transfer modeling, etc., etc. I'm just saying, like it's a big area. I've just compressed it into the scattering matrix formalism, but you can individually model each elements of scattering matrix by going into the geometry and the physics of the problem. Now we come to the decomposition. So any doubt till now? I don't know whether people are sleeping or not. This online format, there is no way to know.
You continue, Sanid. Please continue.
Yeah. Yeah. So yeah, let me take a sip of water. Okay, so we have the scattering matrix, right? I mean, that is the thing we have in the case of polarimetric SAR. Now, how do we extract information out of this? So that is where the decompositions come. So we basically try to apply like a lot of concepts from linear algebra. Like one very basic idea in linear algebra is the idea of Eigen decomposition, right? I mean, you have a matrix, then you find its eigenvalues, find its eigenvectors, and they are some kind of canonical mechanisms, right? To the problem at hand, the eigenvalues and eigenvectors have special meaning. So that is one thing we will come back to. So similar to that, we can apply various concepts. So here, for example, if you take the scattering matrix itself, which is, as I said, is a complex 2 by 2 matrix, then you try to decompose it directly. So as I said, S is a 2 by 2 complex vector, right? So you can find the basis of that vector space. It's a 2 by 2 complex. It's a vector space of 2 by 2 complex numbers. So sorry, 2 by 2 complex matrices. Then one basis is identity comma sigma 1 sigma 2 sigma 3. That is the polyspin matrices, right? So if you decompose your S matrix in this basis, what you end up getting is the poly decomposition. So the polyspin matrices has nothing to do with remote sensing. This comes from quantum mechanics, but I mean the idea is the same. Like you have a 2 by 2 complex matrix, you decompose in some basis. So if you choose this basis, the interesting thing is the coefficients A, B, C, D has physical significance. They are physically meaningful. A, B, and C, for example, A is the old scattering, or the what do you call as the surface scattering. The power in A, the value of A is proportional to the percentage of scattering, which is surface scattering. And C is volume scattering. I mean, as I said earlier, that is the scattering from the bulk. And B is the dihedral scattering. So dihedral is like double bounce. Let's say you have a tree, then you can imagine the wave hitting the tree, then hitting the ground and coming back to you. Two hit, right? So this is the double bounce. It bounces 2 times. Whereas single bounce or odd is like surface scattering. It hit and it comes back to you. There is no second bounce. So physically the A, B, C, D has this kind of meaning if you decompose them. Then you get nice images like this. So this is airborne data from DLR. That's the German space agency. So we got this data. It's an airborne data of some area in Germany, I think Kaufbeuren. We got it through a collaboration with them. And you can see this is after poly decomposition, and this is quite nice. I don't know whether you're able to appreciate this, because see, let's say if this is optical image. Now what does it mean? Yes,
Sanid,
yes,
can I have a query? Actually, you see, the students will possibly understand better if you just say that how the images is formed from poly decomposition. What you are actually doing, or what you are actually trying to show, so that you get this kind of an image. So because you see, most of the students are having idea about the analog images. That means the usual camera images. But
yes,
what
sir.
is that you are printing in the polarimetric so that you get the image? If you
Yes,
can
sir.
clarify that one, it will be better for the students.
Yes, sir. Yes, sir. Very, very nice suggestion. Actually, I wanted some feedback from the students, but I'm not getting anything. So, because I mean, there are different ways to talk about this area. Because I am from physics, I always shift towards that. So, what I'm showing here is, let's assume this is an optical image. You did not know that this was a SAR polarimetrically decomposed image or anything. Obviously, what will you see? I mean, how will you interpret this? You will say that on the ground, for example, this red patch here, the prominent pink patch, you will say there is something pink on the ground, right? Because it's a color. So there is a pink, I don't know, some building or something, which is painted pink. But what we are observing here is, I mean, this has no correlation to that. Blue is not something blue on the ground. Red is not something red on the ground. These are different scattering mechanisms. So as Sir was saying, so what we do is we do this decomposition, then we assume here in this case D to be 0 because we assume something known as monostatic SAR approximation, that is HV and VH are the same, so D goes to 0. Then we have three channels basically A, B, C. Then we put the modulus square because these are complex numbers. Remember, we take the modulus and square them. Then we put them in the RGB channels, the red, blue, and green channels. And this is what we end up getting. So wherever there is wherever there is red is dominating. That means it is the double bounce that is dominating. So double bounce is what I just talked about. That means it goes, it is like it is undergoing two scattering, two bounces. So it's like some erect building or some kind of man-made structure. So you can immediately say that wherever you see pink or red, it is some kind of a erect structure. See, this is a completely different interpretation. And this also, you see a lot of clumpy red, pinkish area. This is a city. That's how we interpret immediately. If you see something like this in the SAR, this is a city. So this, we initially thought this is some orchard, because if you have trees which is like in a, which is arranged in a row, perpendicular to this, parallel to the flight of the aircraft, then since SAR is side looking, you can get double bounce. So we thought this is an orchard, but then we contacted them. We came to know that these are what do you call what is it called, this solar panel. Sorry, I could not remember. So this is a solar panel field. So you can see how nicely it has come, like the double bounce. This entire area, this is like a set of solar panels arranged in a huge ground. So like that you can interpret. And wherever there is green, this is vegetation. This may be similar to optical, because in optical also there are too much vegetation. It will be like greenish. Green would dominate because of the chlorophyll content. But here nothing to do with chlorophyll. That's what I was trying to say. Here, this is not telling you anything about the chlorophyll content. This is just telling you about the shape and orientation of trees. This is a diffuse volume scattering from the bulk of the canopy. So that's why it's green. And blue is surface scattering. It is like either very still water or runway or like fallow fields where there is no vegetation. They will come in blue. So that is what happens if we directly decompose S matrix. Now, if we go one step further, we, as you know, like these quantities S11, S12, S21, S22, the elements of the scattering matrix, they belong to a stochastic process, right? In the ground, things are changing. When you are measuring, there are let's say it's a forest, the leaves are fluctuating in wind, things are changing. It's a very dynamic system. So the S11 and S12, they becomes random variables. And if you just average them, a random zero mean random variable, the average would be 0. You can't do the statistics. So to do the statistics of random variables, you have to do the second order statistics, right? The basic fundamentals. So that's how we go to the C3 and T3 metrics, that are basically nothing but second order moments of these scattering matrix elements. So if you form, there are various ways of forming them. I'm not going into the details. If you form them in this manner, equation 21, what you get is the covariance matrix C3. And if you form them in this manner, you end up getting what is known as the coherency matrix. So only difference here is the basis. One is a polybasis, another is a lexicographic basis. But I mean, this is we just need to understand that they are formed differently, but they have the same statistical information. And the thing is, since the way it is constructed, by construction, they are Hermitian. So they are Hermitian, and Hermitian matrices are very nice, right? Because you are guaranteed to have real eigenvalues, and the eigenvectors are orthogonal and everything. So these are the the next level of decomposition, where what we do, these are known as incoherent decompositions because we have done the averaging. So the coherent nature of S11, S12 no longer holds because of the averaging. So it's incoherent decomposition. And as I said, one important decomposition is the entropy alpha decomposition. So I'm directly coming to this because I mean this is something you can immediately understand. You are given a 3x3 matrix which is Hermitian. The first thing any linear algebra student would think of is to do the eigen decomposition, right? So that is exactly what we are doing here. We do the eigen decomposition of the T3 or C3. Then from the eigen values, you can define some kind of pseudo probability. So lambda I is the ith eigenvalue. So what is the strength of that eigenvalue with respect to the total? So it's like the percentage probability. So that gives you sort of that gives you a set of probability. So if you have a probability, then you have some kind of a random process, some kind of a statistical process going on, and scattering is indeed stochastic process. So this gives you the probability. Now once you have this pseudo probability, you can define entropy, the very definition which is introduced by definition of or entropy. They are all on the same concept, and you can define entropy as the log, the P log P summation. This is the entropy. And or you can also define an angle known as alpha angle. I will not go into the details. You have to do a parameterization of the eigenvectors. So so you have these two parameters, which is like now derived out of T3 or C3 matrices, right? So these are polarimetric parameters. We have defined them over this, and they also contain a lot of physical meaning. So entropy and alpha gives you this 2D plane, and it gives you this parabola in that plane. And which region you are, like you are given a data, you estimated the entropy and alpha angle using these equations. Then you saw that it is in the region 7. That means it is low entropy and high alpha. Then you are in a dihedral reflector domain. So you see these two values, the phase space of these two values gives you a direct insight into the physics of the scattering and also about the stochastic nature of the scattering. If you have a high entropy, that means the scattering is highly random. There is no single process behind it. It's completely random. But whereas if it is low entropy, it's sort of deterministic. One process like Bragg scattering or double bounds. One thing is dominating. There is a single mechanism involved. So like that, I mean, this is a very nice interpretational tool for you to understand. And you can also devise, because this is completely independent of any ground data. We have not told our classifier what is on the ground. This is completely unsupervised. So you can devise unsupervised classifiers based on H alpha decomposition. Now there's one more dimension of anisotropy. I'm not going into that because so it becomes hyper. It's a paraboloid of revolution, not a parabol. So I mean, I'll just introduce some of the work we have been doing. So this, I mean, this entropy and alpha I just introduced. We use them to classify crops. So as simple as that. So you take the time series of entropy and alpha, and you see them for different crops. You see that some crops are behaving in a particular fashion, another crops are behaving in this another particular fashion with respect to these polarimetric parameters. So you need multi-temporal full pole data. Then you can devise simple rules to classify them, and you can get some good results. And then the third way of extracting information is model based. So as I said earlier, these elements of the scattering matrix and by extension the elements of C3 and T3 matrices can be thought of as results of various polarization states interacting with certain geometries, right? So you can actually model them because you know how to model an electromagnetic wave. You have the Maxwell's equation, and you can also use some reduced empirical formalism, and you know how the scattering works. If you actually model the scattering, then every model will have some model parameters, right, that goes into the model. Then you can the outcome, because outcome are the elements of the scattering matrix or the elements of the C3T3 matrix, and that is directly given to you from the data. So you have some function of f of something 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 is equal to a known value. So what you end up getting is a set of equations with unknown model parameters. Then you can think of inverting the model given the data. And how good the inversion is, that are the issues. And you have a lot of studies doing this, and we are also working on this area. And this is a very interesting one. So one of the model-based decomposition is the Freeman-Durden decomposition, and Yamaguchi 4-component. And after Yamaguchi, we have rotated Yamaguchi. Then we have Yamaguchi with unitary transformation, that is known as G4U. That is by one of our Indian professors, Dr. Gulab Singh from IIT Bombay. That is also a 4-component decomposition. Then going forward, we have 6-component decomposition called 6SD, then 7SD, and we are currently trying to do 9-component decomposition. So just to give an idea, in the case of Yamaguchi, what are the 4 components of the decomposition? So one component is the canopy scatter from a cloud of randomly oriented particles. This we can model. We can model this sort of rigorously. You take the trees, the canopy, to be a collection of spherical scatterers or a collection of cylinders, dielectric cylinders with a distribution for orientation, etc., etc. Then you can rigorously model the scattering, and then you take that scattering output and you compare it with the data. So that is one component. Then there is double bound scattering from orthogonal surfaces. Then the Bragg scatter. So Bragg scatter is a sort of a single scattering, but this is why it's called Bragg scatter, because the theory is very similar to the X-ray Bragg's equation in the X-ray crystallography. So but basically, when you have the wavelength matching some frequency, some inherent wavelength in the scatterer, then you have sort of a coherent backscattering. So that is the Bragg scatter. Then helical is this complex scattering when you have a lot of man-made structures, and this is an extra component added by Yamaguchi. It's not there in Freeman-Durden. But what I'm trying to say is, here we model the scattering directly through equations, models, and then we compare them with the data. So that is the case with model based. So I skip the details. Now let me introduce you to hybrid polarimetry. So till now we were talking about transmitting linear, receiving linear, right? H is transmission, V is receive, H, V. So instead of H or V transmission, suppose we transmit circular. So circular, what I already described, right? So in that case, we have hybrid polarimetry. That is, it's a hybrid between circular and linear. You transmit circular, but you receive linear. So you have RH if you transmit right circular. You have RH, right circular transmit, H receive, RV, right circular transmit, V receive. So in that case, we cannot do a lot of stuff. Like we cannot do the previous poly decomposition. We cannot do Yamaguchi. We cannot do H alpha. We can do H alpha in a different way, but not the way it was introduced there. So instead of that, we have another kind of decompositions known as M delta and M chi decomposition. These are by Keith Rane. He is this father of this hybrid polarimetry. And just why I'm stressing this, because like our sensor, the RISAT, the Indian SAR mission, the first completely indigenous mission, had a hybrid polarimetry capability. So we had a SAR, and it was capable of doing this hybrid pole. And I'll show you some output. I think it is there. So again, theory how to do this. I'll skip all this. So so here you see. So this is RISAT. So RISAT is our satellite. So at least you remember the name of this. This is the radar imaging satellite 1. In the FRS1 mode, it is the fine resolution mode 1. This is a hybrid polarimetry mode. So you can download this data, I think, from NRSC. It's quite, I don't know, I don't think it's open, but it's quite cheap for Indian universities. And you can download them and you can do some studies. And we have done some study between M delta and M chi for some agricultures. And you can see it's quite nice. So it's the hybrid polarimetry, but it looks quite useful, like the decomposed images. Now we have done another study where we compared CP and QP. CP is hybrid polarimetry. Remember, in hybrid polarimetry, that is RHRV or LHLV, we don't get the full scattering matrix. We don't have this S matrix with S11, S12, S21, S22. No, it's not there. So it is reduced. I mean, the information we have is lesser than QP. QP is the quad polarimetry, that is saying also known as full polarimetry. That is what I have been talking about till now, which gives you the full scattering matrix. So people have been arguing CP is to be inferior to QP, but we have done some analysis and we have shown that if, like, for nice features, at least like these kind of very obvious features, the differences between full pole and hybrid pole is not that much. So hybrid pole is quite useful. Now, this is something, if you are a research scholar and trying to do hybrid polarimetry or dual, another situation similar to hybrid polarimetry is dual polarimetry, that is like Sentinel-1. So Sentinel-1 data is free, but remember, it's not full polarimetry. It again will not give you the full scattering matrix, S11, S12, S21, S22. No, it has V transmit and V receive, V transmit and H receive. So it has only the half of it. The coherent system, which is half of the full system. So you have VH and VV, and the phase is there between them. So again, it's sort of a dual polarimetric system. It's not hybrid, it's dual pole, because the transmit and receive both are linear. So you end up getting a C2 matrix, not C3. So now people expand C2 to C3 by assuming something. So this is, I just put it here because this is by Keith Rane. So he was the father of, as I said, the compact polarimetry, the hybrid polarimetry, which is also known as compact polarimetry. So he said, you should not do this. If you expand, this is what he has written. The method is known to not work over terrain with slopes or having elevation variance. There is no way for a user to know if and when to trust the result from pseudo-covariance approach. So pseudo-covariance approach is C2 to C3, this expansion. Because once you have C3, you can do a lot, like H alpha, Freeman-Dud and Yamauchi. So people want C3, but dual pole only give you C2. So they expand pseudo-covariance matrix. So he is saying in a very strong language, all studies based on that expansion are suspect and deserve to be disregarded. So it's a warning for people like Sentinel-1 users who wants to use full polarimetric tools. There are well-tested dual polarimetric tools. Use them. Don't try to expand. So we can do more. So this is again with RISAT data. I just wanted to show you some of our sensors and what we can do with it, because worldwide data is anyway you may be aware of. So this is again using RISAT, and this is from Chota Shigri Glacier. So this kind of a classification of glacier zones, like debris covered, I mean wet, superimposed ice, we can sort of get that information and classification using SAR data. This is not possible with optical. If you see this area, Chota Shigri Glacier, it will just look white. It's a white patch glacier. That's all optical. But with SAR, because of its penetration, its higher wavelength, the way it is sensitive to dielectric constant, density, everything. It gives you that information. So this is what we have been doing. I mean, I am like in the back end of this. Like I try to develop the algorithms which goes into the back end, but the front end is in Java. It's done by one of my colleague. So it's in Java. So this is the software which is now copyrighted, known as microwave data analysis software, or MIDAS. And I encourage like people who are listening to this seminar, like to try to get a copy of this. This is free for Indian users, but you just need to do a registration in an ISRO website. You can download this, and whatever I have been talking about, the theory is actually implemented here. And I mean a lot of it. And since it's our software, you can give us feedback. I mean, it's our in the sense it's Indian, like we have developed it. So like, I mean, I know like there are a lot of options elsewhere, like commercial software also, but this is something you can also try to use and give us feedback so that we can improve on it. And it has this kind of a structure, like we have a C++ backend and a Java GUI. And it supports all the ISRO missions, which is not the case for many even commercial softwares. But I mean, we support all the ISRO missions, even airborne missions, and also ALOS and RadarSat and all those things. These are external. If you don't know, ALOS is a Japanese satellite, RadarSat is a Canadian satellite, UAVSAR is a NASA JPL airborne system. And these decompositions like Freeman-Durden and Yamaguchi, and also G4U, the Yamaguchi with the unitary transformation, and Y4R, that is a Yamaguchi with orthogonal transformation. All that is implemented in MIDAS. So this is one study you see, and also the signatures I was talking about, the polarization synthesis. That module is also there. Like if you give the pixel number, it will give you the plots like this. So you can see the polarization, the signatures change when you go from one land class to the other. But even in the same land class, like these are all urban. Sorry, here it is different, but here it's all single bounds. Like these are all sort of bluish, type 1, type 2, type 3. We don't know what they are, but you can see the signatures are different a little bit. So even within the same class, you have different signatures. So right now we are at SAC, we are working on a technology development program to identify the features from this 3D surface, so that we can have an automated algorithm to classify. So quite challenging work. We are currently trying to do that. So here it is, like urban. These are all urban 1, urban 2, urban 3, but the signatures are not the same, though they have some common characteristics, but they differ. Now there is this idea of polarimetric indices. We don't directly use any decomposition channels or decomposition parameters. We make secondary parameters out of it, like child parameters or derived parameters. So there are things like Canopy structure index, volume scattering index, biomass index, interaction type index, and there are a lot of publications which they use these kind of indices to study. And the most important one is RVI. So the radar vegetation index. There is a non-polarimetric definition and there is a polarimetric definition. So this is what people have been using earlier. If you have the sigma naught, which, as I said earlier, you don't need any polarization, I mean the phase information. You can get from the 4 channels, the power or the amplitude images, you can get this. Whereas this is the polarimetric definition of it by Van Zyl, RVI, and the lambdas are the eigenvalues of C3 matrix. And this is a very good parameter for studying vegetation using radar. And there is this concept of PRV. So the problem with RVI is it's not very meaningful for dual pole. You need full pole and full pole.
Sanid, is
Yes.
there any significance of that number 4 multiplied by 4? Why it is multiplied by 4? Any justification or any?
Hello.
It's an index, right? So I
yes,
am
sir,
assuming
yes, sir.
that it must be between 0 to 1. But if we multiply it by 4, then it may not be between 0 to 1.
Yes, sir. Yes, sir. So RVI, this is not between 0 and 1. This is between, it goes beyond 1, RVI, by this definition. So the reason behind it was some some fitting to some model they were trying to do. Some empirical reason. They wanted the value to scale, to a sensitive value to vegetation, whatever biomass they were trying to correlate with. So it's just a scaling factor. I mean, even without it will work. So this PRVI, this is something which can be used for dual pole. So for sending, you will see a lot of studies using PRVI. It is a very recently introduced one, 2018, and we already use this for in one of our work to study biomass of mangroves in this Mundra area in Gujarat. So me and one of my students, we did this. We use PRVI basically. This and Sentinel and PRVI. And now in the last 5 minutes, I want to introduce this area known as PolInsar. So what happens here is we combine two SAR technologies. One is polarimetry and one is interferometry. Now, interferometry, I did not have any time to talk about. It's another vast area, and one of the important applications of INSAR is the topography. Like when you download this DEM, this the digital elevation models like SRTM. So I mean, there are optical ones too, but the SAR-based ones are quite good because it can penetrate through vegetation and sense the ground in L-band, higher wavelength case. So generally, this kind of topography, surface velocity, and surface deformation, this information can be we can get those information from interferometric SAR. Now, this is sort of an interferometry system, like very similar to what you have studied, this Young's double slit experiment, or where you have these interference patterns. This is very similar to that. Only thing is, instead of a screen where we project these interference patterns, we record them in the SAR images, in basically the face, the black the black arts of face. So the phase record, the phase differences record in the SAR images is what this interferogram is useful. Now the polarimetry, as I already said, gives this scattering metrics, and this provides insight into other kind of stuff like geometry, shape, and dielectric constant. Now when we try to see, what we want to do is we want to get height of, let's say, so this kind of an approach, like where we have a ground and we have vegetation, like we have trees over it. The idea is to get the 3D information. In this case, in the case of PolInsar, we want to know what is the height of the trees. Now let's say we did not have polarimetry, we only had interferometry. Interferometry means we have the phase information, but only there is one channel, that's one polarization. We have HH. So HH transmit and HH receive, H transmit and H receive, they are coherent. That means we are recording the phase, but there is no V channel, only H channel. So in that case, what the problem with trying to get the height is that we don't know from the scattering center, we don't know from where the scattering is happening. It could be from the top of the canopy, it could be from the ground, it could be from somewhere in between. This is the scattering phase center. We call it scattering phase center. So if you have just one polarization channel, that is the case in the normal INSAR, in interferometric SAR, we can get a height. We can invert this height, but it won't be the height of the trees. right? You understand what I'm saying? But where we have different polarization, they sense different portions of the canopy, because HH would be scattering from here, VV would be scattering from somewhere else. HH plus VV, as I said, like we can synthesize all possible transmit and receive combinations, and we can also do the singular value decomposition to get the maximum and minimum and everything. So we can basically go much beyond this. We can get what is the ground scattering, what is the top of the canopy, what is the middle of the canopy. Like, I mean, I'm exaggerating, but what I'm trying to say is you have much more. So you have this kind of, when you have this kind of a situation,
Sanid, are you trying to say that in comparison to INSAR, pole INSAR will be a better estimating the canopy height, is it?
Exactly, sir. Exactly. That's what I am saying. So the INSAR system cannot, basically, because of this problem.
But are you trying to say that pole INSAR will be accurate or more accurate than INSAR?
So pole INSAR would be more accurate than INSAR, but absolute accuracy I'm not commenting on right now.
Okay. Got it. Please go ahead.
Yes, sir. So we can fit a model. So how do we? So this is the concept, basically what I said. Now, how do we do it? We fit a polarimetric canopy scattering model to model the forward scattering. So this is the RVOG approach. It's known as random volume over ground. It has these parameters: height, extinction, and ground contribution. And from data, we have coherence at 3 polarizations. So it's basically 4 polarization, but we are assuming HV to be same as VH. So we have coherence, complex coherence at 3 polarization. So basically we have 6 parameters here and 6 parameters here also in the model, because these are complex. Height is not complex, but these 2 are complex. So this is the more flow of it, where I could not rotate it. So basically you get gamma 1, gamma 2, gamma 3. That is the estimated coherence. Sorry, not estimated. This is from the data from the T. So here in the case of pole INSAR, instead of T3, we have a 6x6 matrix known as T6. And then we have the RVOG model, which contains the height of the canopy, sigma is the extinction, and mi is the ground scattering ratio. So then from this model also we can get gamma 2, gamma 1, gamma 2, gamma 3 coherences. Then we sort of do an inversion. So the inversion is the tricky part, but there are various approaches to it. One is known as the 3-stage inversion. This is quite popular. So this is sort of a geometric approach where we try to put these coherences inside a unit circle in complex plane. Then we try to first fit a line to get the ground phase. I mean, what would be the phase if the scattering is from the ground? This we can extrapolate and get, you see, like we put the different gammas, gamma 1, gamma 2, gamma 3 directly, or then we do a sort of singular value decomposition and get them and put them, try to put them in a line. They won't lie on a line, like they'll be here and there, but then you fit a line. Then wherever that line hit this complex, the periphery of this unit circle, one of them is the ground phase. Then you plot a family of curves, f of h sigma. Then you will see they will be circling like this, and wherever this hit the highest, I mean the farthest point from the ground topography, that is your inversion point. So we have implemented this algorithm actually. So this was one study like I did recently. The study area was in Saipung forest in Meghalaya. So this was quite an interesting work. Like I went to this forest. It was a very like pristine, very dense forest. Like we stayed inside the forest for 2-3 days. I mean 3-4 days to do the measurement of canopies. Then we purchased an ALOS pulsar data over this pole INSAR data that we need fully polarimetric and bitemporal, like we need it for 2 times. Then then we inverted the, so this is the kind of situation we will get, as I was talking about when we do the 3-stage inversion. And we got somewhat good, yeah, some 0.8 R2 with the ground truth height. So this is another, so the height inversion is another interesting area of advanced area of SAR polarimetry. And I'm just touching, I mean, I'm just, this is a very surface level talk, like I just wanted to give you glimpses of it. But there are like thousands of applications where SAR polarimetry is used, and our department and Suman Mitra sir, like we are having a collaboration where we are using the statistical properties of the T3 and C3, these matrices. I mean, the probability distribution of them, I mean, they follow the Wishart distribution. And we are trying to use that to do a better classification than traditional techniques. And I mean, it's a very vast area. It's very interdisciplinary. If you are from physics, mathematics, computer science, engineering, I don't know. I mean, any area, like you have something here. So I think I'll stop. I think it's time. So if there are any questions, I'll take. Thank you so much.
Thank you, Dr. Sanid, for this talk. Is there any question?
Yes, sir. I have one question. So, for generating full pole image from, say, some kind of single polarization image, if you are considering on an HH or HV, is it possible to introduce some kind of neural network there for, we can extract features and we can use some kind of translation for generating full pole image, full pole SAR?
So first of all, I am not an expert in machine learning. Like I have no idea, but I mean, in principle, what you are saying shouldn't be possible, because you are talking about generating information where, I mean, unless you have some other ways of providing that information, like some other channel, I don't think this is possible. Like, but I mean, if you have some, let's say, some archival data of other channels, for let's say there is like T1, T2, T3, like lot of temporal data, and you have full pole data for other dates, and in between for one time you have a single channel, you don't have other channels, then yeah, definitely I think the networks would be able to reconstruct it.
Okay.
I don't know, there may be some other people who will be able to answer it better.
My understanding is that if you do not have anything, and from the half information you cannot actually get into the full information. That is impossible. So as Sanid said, some kind of interpolation is possible. Some kind of interpolation is possible. Interpolation means you know some initial information, some end information, and then you are interpolating. That is possible. But if you have only some initial, yes, and you want to only do some end point, that is some kind of an extrapolation. This extrapolation may not be very good for this kind of a problem. That is what my understanding is. I'm not very sure, but extrapolation will be a difficult task.
Okay. Okay, sir. Thank you.
Again, you can try it out, but I don't think that it will give you a very accurate result on that. I have one or two queries. I think I mostly try to see it from students' point of view and asking questions to the speakers. So, Sanid, can you give us little bit glimpses that which are the Indian satellites having this kind of SAR imaging technique, and what are the target area they are targeting and giving back to us? And what are the little bit applications that is very important about it? And the last question is that among the pulsar, full pulsar, INSAR, pole INSAR, is there any demarcation that this possibly is very good as far as information content is concerned?
Yes, sir. I mean, they are both excellent questions. I mean, so first let me take the Indian satellite scenario. I mean, I'm very happy that you asked this, sir, because I mean, we have this Sentinel. I mean, people are aware of Sentinel, ALOS, radar set. So, I mean, I have. I mean, already introduced RISAT-1, so Radar Imaging Satellite 1, and we have a lot of archival data with NRSC. So NRSC is the ISRO Center, National Remote Sensing Center in Hyderabad. So I would encourage these institutes to go to their archive and download it. It's very cheap as far as I know for Indians. And you have, as I said, the hybrid polarimetry data there. We don't have full pole. And unfortunately, RISAT-1 is not functional now. It is not giving, I mean, there was some incident earlier and it's decommissioned as far as I know. But we have a lot of archival data. Then RISAT is it's a series, RISAT series. Then RISAT 2B is in the orbit, but it is not a civilian satellite. It is for military. Then RISAT 1A, that is the civilian follow-up mission for RISAT 1, is going to be launched. So there, I think the payload, everything has, I mean, already the hardware is already there. It just need to be launched. I don't know the exact launch date, but you can follow it up RISAT 1A, and that will have full polarimetry. So we will be having a lot of data. Then I just want to introduce to this very interesting mission which is going to come up. It is a collaboration between NASA and ISRO. It is known as NISR, NASA ISRO Synthetic Aperture Radar. So there are two. It's a dual frequency SAR system. The L band is from NASA JPL, and the S band, it's an L and S band. S band is from ISRO, and L band NASA is making. S band ISRO has already made, and we will be launching it. The GSLV rocket will be launching it in the next year, hopefully. So this will give you free data. So the data policy is completely open, both from NASA and ISRO side. The whatever data, full pole, half pole, dual pole, everything would be available for free worldwide. So these are the 2-3 missions which I can think of right now. Now, regarding the, I'm sorry, sir, what was the second question?
Second question was that as far as information is concerned, so which kind of SAR image is having the best kind of an information content?
Yes, sir. Yes, sir. So,
or can we say something or no? It is not possible.
Yeah, so there are two ways of looking into that problem. See, as I said, for INSAR applications, like if you want a digital terrain model or if we want to see the surface deformation, fully polarimetric data is not required. There the importance is the consistency of the same channel over and over again. So this suppose we want to monitor earthquake, for example. So let's say we have HH channel, but we need HH continuously every, let's say 12 days. We want the continuous monitoring of that area to generate a set of interferograms. Then from the time series of that interferograms, we will predict whether the earth, the crust is going up or going down. I mean, the deformation, how it is going. For that application, I would say single channel SAR is the best. But for example, if I want to study biomass of a forest, that means I need to know the precise information of the height, the various other parameters like canopy structure or the DBH, the diameter of or the girth of the trees. Then for that application, fully polarimetric data is the best. Then there are a lot of ocean applications where dual pole data is considered to be the best case scenario. But from a purely theoretical point of view, information content wise, dual pole, the full pole data gives the maximum information possible.
Okay. Okay. And right now you are working on that mangrove in the Gujarat coast area, right?
That study is over, sir. Like we did it in last 2 years.
Okay.
So that is completely.
And do you have the data for that one?
That was Sentinel one. We used the freely available data.
Okay. Freely available data. Maybe I will talk to you later on about that.
Sure, sir.
Okay. Thank you, Sanid. Thank you.
Thank you so much, sir. So, I would suggest students, who have any questions, you have my email ID. You free to write to me, and thank you for having me.
Peter, do you have any question? You have raised your hand. No. Okay. So, Dr. Sanid, I have one small question. Like,
Yes,
can we kind of fuse optical data with polarimetric data and improve like classification accuracy?
Yes, sir. So this is a very current hot area. So like that was what I was doing in this Trento University, like through that collaboration. So we were trying to fuse SAR data, the full pole SAR with optical. So the question is how. So that get us into the current technologies, and myself I am not sure which one is the best technique. So we were trying to use a sort of formalism, not a machine learning technique, but sort of a formalism based approach to do that. But this is one current area, very much current. So I don't know, like whether any correct answer I can give you now.
Okay. Thank you for sharing your thoughts. Now, I would like to present a small memento to you.
So thank you, Dr. Sanid. This is from our IEEE SPS Gujarat chapter and from the Dhirubhai Ambani Institute.
Sir, I think I'm on audio only mode. Should I come in video?
Yes, you need to come.
Actually, then I will have to exit and join again, I think.
Okay, no issue. You can left and again join again.
Yes, sir. Yes.
So far, Manish, we have covered 4 sessions, right?
Yeah, sir. Up to this time, we have covered 4 sessions.
4 sessions, but I'm little bit surprised that participants are not asking questions. I am only asking most of the questions. That is not good.
Participants asked question only yesterday in first session, and today in the first session 2 or 3 questions they have asked.
I think they are feeling hungry. After having lunch, they will be recharged again.
We hope that they will ask the.
So after lunch, it is Gaurav or no?
Sir, after lunch, first talk from the Preeti Khanna, IIIT Jabalpur.
Okay.
Then second talk from the Gaurav Harit. Then third from the Springer, and evening talk that is from the Ishwar Sethi, Auckland University, USA.
Right. Oh, Sanid is here. So Sanid, can you see your memento?
Yes, sir. Can you see me?
Yes. We can see you.
Hello, sir. So it was a nice experience giving the talk, but I am a little disappointed. Nobody asked any questions.
Right. I told the same thing. Students, maybe most of the participants, they are trying to digest. Maybe it will take some more time for them to digest.
Yes,
that's why we are recording all the session, and the recording will be available to all the participants. So they can look back at the recording and then try to understand the delivery or the kind of problem that the speakers they throw to the audience.
Okay, sir. So thank you for the memento. It's quite nice.
Thank you. Thank you.
So before closing the event, I request to all participants, please open your video camera so that we can take one screen. Yes, thank you. So
Okay,
thank
sir.
you everyone. We will meet again at 2:30 p.m.
Okay.
with the next talk that is on the biometric system.
Okay. 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 Thank you.
Thank you. Thank you all.
Thank you, sir.
Thank
I'll
you.
exit now.
Okay, sure. We will all exit. And we'll come back at 2:30.
Yes, we will need to come at 2:30.